Welcome to the second part of today's lecture. Before continuing with the lecture, let me review the steps that we need in a statistical project. We start with specifying the questions that need to be investigated using data. After that, we specify the population and the statistical variables of interest. Then we collect data either from the sample or from the population on the specified statistical variables of interest. Once we have collected data, we try to organize and clean it. After the data is being cleaned, then we go for the analysis of those data collected on the specified variables. In the analysis step, so far we have seen univariate descriptive techniques such as frequency table, graphical techniques, and numerical techniques. In numerical techniques, we have seen a set of numerical techniques to find the location of different critical observations, such as center. In addition to that, we have seen a set of other numerical measures to find the amount of variation in our data. Next, we try to see another set of numerical measures to check the shape of the distribution of the data that we have collected on certain variables. The distribution of the data that we have collected on certain variables can be or can have any shape. In order to check or study the shape of the distribution, first we need to define a reference distribution against which we can compare the distribution of the data that we have collected on certain variables. The reference distribution that we want to define is the one which is balanced in all aspects. Such a distribution we call a normal distribution. The density or the histogram of a normal distribution looks like this. As you can see, this is a balanced symmetric distribution, which we call it normal distribution. For a given a statistical variable x, if the histogram or the density plot looks something like this, we say that the variable x is normally distributed, and we show it as x distributed normally with mean m and standard deviation st. That means a normal distribution is being characterized by the mean and standard deviation having this symmetric shape. One way to test the normality or in general the distribution of a given variable is to plot its histogram or density. Another way is to use numerical measures. First technique is to compare the mean of the variable against its median. Now, if mean is equal to median, which is this case, if mean is equal to median, the distribution of the variable is symmetric, like the one in the middle here. If median is smaller than mean, then we have a higher density at the left side, a higher density at the left side, and a longer tail at the right side. That's the distribution that we have here on the right-hand side. Now, if median is larger than mean, we have a higher density at the right side here and a longer tail at the left. That's the distribution at the left side. Now, in addition to comparing the mean and median, we have specifically numerical techniques that specify the shape of the distribution. The first one is skewness. Skewness, as you can see, the formula is n divided by n minus 1 times n minus 2, the sum of observations minus the mean divided by the standard deviation. This is the standard deviation, everything to the power 3. Now, if we have skewness equals to 0, that's a symmetric distribution, a symmetric normal distribution. If skewness is a negative, we have a long tail at the left, that's skewed left. If skewness is positive, we have a longer tail at the right hand side. The second measure which we use in order to specify the shape of the distribution, is called kurtosis. As you can see, the kurtosis is being calculated using this formula: n times n plus 1 divided by n minus 1 times n minus 2 times n minus 3, the sum of each observation minus mean divided by standard deviation to the power 4, minus 3 times n minus 1 all square, n minus 2 divided by times n minus 2 times n minus 3. That's the kurtosis. If kurtosis is equal to 0, we have a normal peak. If kurtosis is negative, we have a heavier tail, more flatter distribution. If kurtosis is positive, we have a sharper peak. Together, skewness and kurtosis gives us an idea about the shape of the distribution of a given variable. The more the skewness and kurtosis get closer to 0, the more our distribution gets closer to a symmetric distribution. Else, the distribution departs from symmetric distribution. In case of outliers, it's good to remove the outliers first, then check skewness and kurtosis for their shape.